Welcome to the Deep Dive, the shortcut to understanding the most complex ideas in engineering and technology. Today, we are strapping in for a deep dive into the brain of modern automation. We're talking about mechatronic systems design, or MSD. I mean, just think about the machines that define our world now. Industrial robots that can paint a car with, micrometer precision, or that sophisticated medical equipment in a hospital. None of these are just mechanical things with a few wires plugged in. They're holistic systems. So our mission today is to really break down this engineering philosophy, mechatronics. We want to move past seeing these systems as just a box of parts and really get a feel for the integrated, the synergistic design lifecycle. We're going to follow the whole process, right from the first idea through choosing components all the way to, the final handshake on the factory floor.
It really is a paradigm shift. And I think understanding that shift is the key thing here. If you look at conventional machine design, the kind of stuff that powered the early 20th century, it was all inherently bulky. You had this reliance on really complex mechanical systems, and precision was achieved by, well, brute force, by incredibly narrow and expensive machining tolerances. Mechatronic design is the complete counterpoint to that. It is all about integration, the seamless blending of hardware and software. And what you get are these compact systems with mechanically simpler designs. And here's the crucial part. They get their precision not from that expensive metalwork, but from continuous high-speed digital feedback control. They're constantly measuring and adjusting.
Okay, let's unpack this because that idea right there, shifting the burden of precision from the physical metal to the software, that's the genesis of this whole field, isn't it? It just
Okay.
fundamentally changes the cost, the flexibility, everything about the machine. So when we talk about mechatronics as this philosophy, we're really talking about the integration of three core disciplines, all happening at once. First, you've got the foundation, the mechanics. This is your physical structure, the machines, the precision mechanics, the bones of the thing.
Right. And then you layer on the electronics. That's your microelectronics, power components, and critically, the sensors and actuators, the parts that let the machine see and act on the world.
And finally, the architect, the information technology. So system theory, mathematical modeling, automation logic, and of course, the software that ties it all together. And the key is that it isn't sequential. You don't build the body, then bolt on the brain. They're engineered at the same time.
That concurrent nature is exactly why the design process is, well, nonlinear. The whole goal is what we call concurrent engineering. You're blending design and manufacturing considerations right from the start. It optimizes everything, and it just drastically cuts down development time. You don't have one team sitting around waiting for another to finish.
That sounds great in theory, but I mean, in practice, doesn't that get a little chaotic? If everyone's working at the same time, how do you make sure the core logic is even sound before you start spending money on hardware?
That's where the discipline of stepwise refinement in software comes in. It's a very structured process. You start with the purest form of logic, which is the math, the control laws. Then you refine those mathematical formulas into efficient algorithms. And here's the key discipline. You simulate and verify after every single refinement step, long before it becomes actual code.
So you're basically testing the physics and the math before you're even thinking about a line of C++ to.
Exactly. The whole design has to start with physical systems modeling. You have to understand the dynamics of your mechanical structure first. And often that means simplifying a really complex system down to a linearized model, which is just much easier to design the control law for. Because if your model is wrong, your control law will be wrong, no matter how elegant your code is.
Okay, so let's move from the abstract models to the actual physical parts. Every mechatronic system has to sense and it has to move. Let's start with the movement, the actuators, the muscles doing the work.
Right. Actuators are essentially transducers. They turn energy, usually electrical, into a mechanical output: force, motion, position. And we generally classify them into three main groups that a designer will choose from. It all depends on the force, the speed, and the precision needed. The first, and by far the most common, is electromagnetic. So your AC and DC motors, stepper motors, they're clean, they offer amazing control. The second group is fluid power, hydraulics and pneumatics. These give you just massive force density, but they can be a bit harder to control precisely.
And then the third group is what you call unconventional. This is the really interesting stuff. Piezoelectric materials that change shape with voltage or shape memory metals. These are for really small, really high frequency kinds of tasks, right? Micropositioning. And I think the insight here isn't just knowing the three types, it's understanding how digital control lets us get incredible performance out of them. I mean, take a complex hydraulic system. With digital feedback, you're constantly making these tiny adjustments to the fluid flow to prevent overshoot. You get this smooth, repeatable motion that old school mechanical valves could just never dream of.
That's it. The
Yeah.
system's reliability comes from its ability to constantly correct itself. And
Uh,
to do that, it needs good data. So that brings us to the sensors, the nerves of the system.
Yeah, sensors convert physical inputs, position, pressure, temperature, force, flow, you name it, into an electrical signal for the controller. And the sheer variety is staggering. But the selection criteria, that's what makes or breaks a design. Right, because for the engineer planning this, they need to get the trade-offs right. It's not about just grabbing the most accurate sensor off the shelf. It's about what the system actually needs.
Absolutely. The first big one is accuracy and sensitivity. Accuracy is pretty simple. How close is the reading to the real value? But sensitivity is so important in automation. It's the ability to see tiny changes. If you're monitoring, say, turbulence in a fluid or a subtle vibration in a machine, you need high sensitivity. It's non-negotiable.
Okay, and then you have to consider response speed, and I think most people hear that and just think, how fast does it give me a number? But you're saying it's more complex than that.
It is. A good designer looks at 3 speeds. Time to the first reading, yes, but also the recovery time after a big change. And crucially, the time it takes for that reading to fully stabilize and become accurate. If your machine is updating 50 times a second, but your sensor takes 100 milliseconds to stabilize, you're basically getting garbage data half the time.
That is a classic design trap. And speaking of data, linearity seems like it would be critical for just simplifying everything downstream.
It's vital. Linearity is just how proportionally the output signal changes with the input. If a sensor is highly linear, processing the data is easy. Double the input, you get double the output. Simple math. If it's nonlinear, you suddenly need complex lookup tables or correction factors in your software. It adds loads, it adds potential for errors.
And finally, the one that feels obvious but probably tricks people up in the real world all the time, environmental durability. And you say you have to define this in 3 different ways.
Yes, you do. Because a sensor might be electrically durable, it can handle voltage spikes, but it might be physically fragile. Physical durability is about withstanding vibration or dirt or pressure. And chemical durability means it can work in extreme heat or with corrosive salt spray or around hazardous materials. You miss just one of those 3, and your multi-million-dollar machine grinds to a halt because of a $100 sensor.
So that brings us from the muscles and nerves to the brain itself, the controller hardware. And this is where designers often face that big debate, PLC versus an embedded system.
It really boils down to reliability versus flexibility and cost. PLCs, programmable logic controllers, are the absolute workhorses of industry. Their strengths are obvious, they're incredibly rugged, they're reliable in really harsh environments, and they have a modular structure. A card fails, you just swap it out, it's easy.
Plus, they use simpler programming languages like ladder logic, so maintenance staff can usually handle them. And a big brand PLC comes already certified for safety standards like CE marking.
But then you have embedded systems, microcontrollers, single-board computers, and they have huge advantages in cost. Sometimes just 20% of the price of a PLC. They're compact, they need less cabling, which is a big deal. Less cable means better signal quality and less chance of EMI.
Hold on, let's pause on EMI for a second. For listeners who haven't been on a noisy factory floor, what exactly is EMI, electromagnetic interference? Why is it such a villain for these systems?
Good question. EMI is basically electrical noise that's generated by all the high-power equipment around. Think massive motors starting up, big welders running. This noise is like static on a radio. It can corrupt those tiny low-voltage signals from your sensors. And if your system isn't shielded properly, that noise can cause random intermittent failures, an absolute nightmare to troubleshoot, which is one reason PLCs, with their heavy-duty shielding, are still so popular. But whichever hardware you choose, you still need sophisticated software. We already said mathematical models are key for the initial design, but simulation, that's the bridge you need to get from the math to the real world.
And we've got 2 big real-time simulation techniques here that designers use. The first is control prototyping.
Right. Control prototyping is where you test a new, complex control algorithm on some real-time hardware, like an off-the-shelf processor. But, and this is the key, the actual process, the actuators, the sensors, those are all real. You're running the real machine, but with an experimental brain. It proves your code works under real mechanical stress.
And then the second, even more rigorous method is hardware-in-the-loop simulation, HIL. Why would a company spend millions setting up an HIL rig?
It's pure risk mitigation.
Yeah.
In HL, you take the actual final production controller, the real hardware and software, and you connect it to a simulation of all the other parts. Virtual models of the actuators, the sensors, the whole physical plant. This lets you test failure scenarios that would be way too dangerous or expensive to try on a real machine. You can simulate a catastrophic power failure or mechanical jam without actually blowing up your prototype.
That makes total sense. You're stress testing the brain under fire before it ever ships.
Precisely. And once that design is validated, you move toward deployment, and that's where safety and standards take over. For any industrial machine in that low voltage range, so under 1,000 volt AC, the Bedrock safety standard is IEC 60204. This isn't just some document you check off. It is the blueprint for preventing catastrophic electrical failures.
And what are the biggest non-negotiables in that standard that designers absolutely have to get right?
Oh, it covers protective bonding, ensuring electromagnetic compatibility to keep that EMI chaos down, and overcurrent protection. And critically, it defines the architecture for your fail-safes, things like safe torque off and your emergency stop functions. Designers spend a huge amount of time on this because ultimately the liability for the system hinges on getting it right. And related to that, when you're installing this stuff, verification tests are critical. For instance, before you power up, you have to do a Megger test on big motors.
A Megger test, that sounds intimidating. What is it actually doing?
It's just an insulation resistance test.
Yeah.
You use a special meter, a megahometer, and apply a high DC voltage to the motor windings. It checks to see if the electrical insulation is still intact, that it hasn't been damaged by moisture or heat, because if that insulation is compromised, the motor will short out and fail the second you start it up. A Megger test prevents a massive, totally avoidable failure.
That is a practical nugget right there. And as these systems get more complex, the documentation becomes the backbone for everything else. We're talking industrial electrical wiring diagrams, detailed schematics with standardized symbols.
And this is where modern software is just essential. You need dedicated electrical CAD software. It doesn't just draw lines, it performs automated error checking. It'll catch mistakes like a mislabeled component before a single wire is even cut.
Right, and these tools handle all the tedious but critical stuff too. Generating the bill of materials, cross-referencing all the components, even optimizing the physical cable routes.
Yeah.
And that last part, it's surprisingly valuable. Using those tools to calculate copper demand and tray fill rates saves a fortune in material costs, and it prevents overheating.
Which brings us to the final crucial step, commissioning. This is the handoff, the whole cycle of testing, validating, running, and then finally handing the system over to the customer. And it requires technical skill and, honestly, an equal amount of people skills. The first job is just verifying the installation quality. You check that all the remote I/O devices are installed correctly. Is the earthing right? Everything has to be physically sound before you even think about powering it on.
And what's the one checklist item that gets overlooked but causes all those weird noise problems?
Verifying the earthing integrity across the whole facility. If you have ground loops or poor bonding, you're going to get noise in your signals. So before startup, you have to check that the earth connections are solid and give you a clean, zero-noise reference point.
And beyond the technical checks, you're saying the human element is just as important during commissioning.
Oh, absolutely. You have to continuously involve the customer's operators during this phase. They need to get familiar with the system while it's being validated.
Right.
Having their support just makes the whole task smoother, and it guarantees that when you leave, the system is being run by people who actually know what they're doing.
So to wrap up our deep dive on mechatronic systems design, the core takeaway really seems to be this. Designers have to abandon that old sequential way of thinking. You have to consider the software, the mechanics, and the compliance all at the same time. If you don't, the whole thing just won't meet its cost or performance goals.
That synergistic, integrated design, that is the future. It leads directly to these intelligent, flexible systems that can do multi-level control, from low-level things like damping all the way up to high-level functions like fault diagnosis, optimization, even learning abilities. It just completely surpasses the fixed, rigid capabilities of conventional machines.
It's a story of how integration really does create intelligence, which leaves me with one final thought. If sophisticated tools already exist to turn these complex mathematical control laws into efficient computer code, how much further will future mechatronic systems go in relying on automatically generated code instead of manual low-level programming skills? Something for you to chew on as automation continues to accelerate.